So,
Recording.
So our next speaker is Professor Lionel Rosier from Université do Litoral Côte d'Opale, and he's going to talk about Kirchhoff formula and numerical control of the wave equation.
okay, first, I apologize for the delay. There was some problem of connection with Zoom. And I would like first to thank the organizer for their kind invitation, and also to thank Ademir Pazotto for the introduction. So I will talk about some recent subjects that I investigate with many people. So it's about the use of Kirchhoff formula in control theory. And the idea actually is to try to extend to the dimension 3 result we have in dimension 1 with D'Alembert formula. So the classical control problem for the wave equation we are considering is the following. So we consider, okay, the wave equation with a constant coefficient on some domain omega, where omega is a smooth bounded open set in R3. And we denote by gamma the boundary of omega, and we have a subset of gamma which is denoted by gamma 0, on which we will have some control, which will be active. So we have some control active on gamma 0 and elsewhere. So u is 0. And the issue is starting from u0, u1, is it possible to arrive to 0 at time capital T? So this is classical null controllability of the wave equation, which is equivalent to the exact controllability due to the fact that the equation is reversible. Of course, this equation was investigated both theoretically and numerically. So for theoretical result, you have the classical work by Bartos-Lebon-Roche in 1992, and we have also some extension by Burke in 1997 for geometries that are not smooth. For the numerics, the first contribution was due to Glowinski-Lyons in the 19th, and you have many contributions by Lebon, Zoazoua, Mikou, Munch, Zoazoua, Vedosa, Zoazoua, and many people, and still up to the last years. And these numerical results are essentially in dimension less than 2, and they all use duality argument. And so more or less you have to use HUM, the Hilbert uniqueness method of Jacques Louis-Lyons, and you use numerics for that. But you have also results that are not based on the duality approach due to Pedragal, Periago, and Villena in 2008. And also in dimension 1, I refer you to the milestone by Jean-Michel just before. So you can have a stabilization and also infinite time of system of PDE in dimension 1. And so, of course, when you have the finite time stabilization, you have as well exact controllability. You have the null controllability, okay? So it was done by Coron, Vasquez, Christic, Bastin, and so they use also backstepping approach to balance the existence of coupling terms. And we use it as well with Perola in 2014. And more recently, so we investigated the problem of the null controllability of a nonlinear wave equation. So this one, so the joint work with Marcelo and Valeria Cavalcanti and Carole Rosier. And so we use a Picard iteration scheme to solve the numerical problem of the controllability to 0 of this kind of nonlinear equation. So in dimension 1, it works quite well. So let's go now to the classical Kirchhoff formula, which is that you can find this kind of thing in a classical textbook, like PD's book of events, but also in more older books by Courant Hilbert, for instance. So this Kirchhoff formula is a sort of extension of D'Alembert formula to the dimension 3. So you look at a smooth solution of the wave equation in R3, so in the whole space, and you start from U0, U1, and we know that the solution to this wave equation is given by the sum of these two terms. So one term is sort of mean of u1, that is initial velocity over sphere. And the second term is a derivative in time of the sort of means of the u0, which is the initial value of the function. And so you have the sum of two terms. Actually, you can compute this derivative in time, and you can put all these two terms into one term, where you still integrate over a sphere centered at x and of radius t. You have, okay, this integral, okay? So it's a representation of the solution. And thanks to it, you obtain immediately Huygens principle that I will state in the following way. For any xt in R3 times R plus, if the initial data u0 and u1 and also the gradient for u0 is 0 in the sphere centered at x and of radius t, then u is 0 at xt, okay? This is, okay, a way to express Huygens principle at fixed time t. And of course, these things has implication for the control that is written in blue. So if you assume that the initial data u0 and u1 have a compact support in some compact set K, and if the time capital T is larger than the diameter of K, then you can you infer from this that u is 0 for x in K and T larger than capital T. So immediately, and without any work, you can say that, okay, if you take as for omega the interior of K, so if you have a control which is distributed on the whole boundary, okay, you know that from this that, okay, you can achieve the null controllability in time capital T. But of course, it's not interesting because you control on the whole boundary. And what we want to see is, okay, can we have similar result with the control on the subset of the boundary? So to do that, of course, we need to extend Huygens principle of Kirchhoff formula to subset of R3, right? Okay, so the first thing to do is to see what happens on half space. So half space, here it will be omega is 0 times plus infinity times 0 plus infinity times R2, okay? So we restrict to the states to the point x for which x1 is strictly positive. So we want to solve this wave equation in this domain. And we take, of course, the homogeneous Dirichlet boundary condition on x1 equals 0. And okay, we want to solve it. Well, how to make it? So I had to introduce a few notation, but this notation will be useful later on. So I think it's worth to pass some time about that. So if x is a point, we write S1 of x, it is the symmetry of x with respect to the plane x1 equals 0. So it is this point here, okay? We make this symmetry. So we denote by sigma plus, it is the intersection of the sphere centered at x and reduced t with the half space x1 strictly positive. So in this picture, it is just here, okay? And sigma minus, so it will be the intersection with the half space of now the sphere centered as S1 of x and with the same radius. Okay, so here it will be this part of the sphere, okay? And so we say that sigma is sigma plus if the time is small. So actually at the beginning, when you consider the sphere, before you have a contact, before you have intersection with this plane, you have the complete sphere. So sigma will be sigma plus. And when you have a contact, when you have some intersection with this plane, you will say that sigma is sigma plus union sigma minus, okay? So we'll have this set. So sigma actually is a wavefront. It is a wavefront. And in addition, you have to introduce the notation epsilon. Epsilon is 1 in sigma plus, and it is -1 in sigma minus. So with this notation, we have the following Kirchhoff formula for the solution of the wave equation in the half space. We have a formula quite similar to the previous one. So we have two terms, two integral. Now we don't compute the integral over sphere, but over wavefront. And now we have also to add the function epsilon, which is 1 or -1. And we have to introduce this function in the integral. And actually, we did use this formula from the previous one just by using a parity argument. And so it's a consequence of the previous one just by using a parity argument. Okay. And by using this formula, actually, and this principle, actually, we can already obtain a good result for, in the case of a box in R3. So we consider the case where omega is the product of these three intervals. This is also the control, the domain of the solution. And for the control, we will take three sides. So this part corresponds, so this size, so when x1 equals 0 or x2 equals 0 or x3 equals 0, it is a part of the boundary where we don't have any control, that is, the solution is 0, okay? And so you control on these three other sides that are not denoted here. So you can use Huygens principle, and actually, so you just extend your solution as odd function in x1, x2, x3, and this way you can recover the exact controllability, but more important, you can do numerics. And for the numerics, we did the following. So we pick L1 equal L2, L3 equal 1/2. We expand the initial data as Fourier series. And here we pick 50 modes in each direction. As initial data, we have considered this Gaussian for U0 and U1 is 0. And actually, we can represent the solution as Fourier series, completely easy to do. It's very easy. But of course, to do the computation, you have to compute the Fourier modes. And actually, we have a lot because we have 50 to the 3 Fourier mode of the initial data. And to do that, we use the trapezoid rule. And we obtain this result. So don't forget that we are working in dimension 3 for the space. So U depends on x1, x2, x3, and time. And so, of course, it's difficult to represent the solution. And so we have to cut, in some sense, we fix one variable, x3. And so we have the solution in terms of x1 and x2. It's more easy to represent this way for different time. Okay, so this is the initial condition for x3 equal 1/4. And okay, this is a Gaussian, of course. So we compute our Fourier series, we consider partial sum. And what we see, of course, we have propagation of waves, which is completely normal, of course. And okay, at this time here, what you see is that in the domain of interest, which is 0, 1/2 times 0, 1/2 here, everything is 0, which is good. Okay, and so we have the null controllability in this domain. Of course, it is not in the whole domain because we have the propagation of wave. But in this approach, actually, we have two domains. You have the domain in which you investigate your control problem, and you have a bigger domain in which you do the computations. Okay, and so you have a propagation of waves, even if actually we use Fourier series. Okay, we didn't use finite element or finite difference. Okay, so in our skiff, we don't have naturally the propagation. But here we see that we have the propagation. It means that the computation are okay. And if we look at the L infinity norm of U on the box 0, 1/2 to the 3, we find this curve. Okay, so the L infinity norm is 0 in the sharp control time, t, which is the square root of 3, which is completely normal. And actually, we find numerically something which is of the order 10 to the -5, which is very good. Okay, okay, so it works well. Okay, but now let's go back to the original problem. Okay, so we want to do the same now in a quite general geometry. So we want to investigate, okay, our control problem. So we have two sets, as I said to you. You have the small set omega, in which you want to solve the control problem. So you have this part of the boundary where you apply the control, and you have this part of the boundary where U is 0. You don't have any control. And the idea is to put this set in a larger one, which is denoted omega hat. Okay, so, and we have to do some assumptions. So actually, omega is included in omega hat, which is included in omega 1. And omega 1 is a big open set, which is delimited by some surface capital S. Capital S is unbounded, and capital S contain this part of the boundary of omega where there is no control, okay? So we assume that in omega 1, we have the Huygens principle. We need to have a Huygens principle in this open set. And finally, for the computation, we need that the distance from this boundary to this one is large enough so that when you do the computation, so wave will propagate this way and we will have a reflection, and we don't want to see the wave again. So, okay, we need this distance to be large enough. This is the strategy, okay? Okay, so now, of course, we have to focus on the Huygens principle in the big set, omega 1, and so we have to justify it. And for the moment, the only way we found was to use Kirchhoff formula. So I have to introduce some notation. So we denote by S2 the set of direction Z of norm 1. When x0 in the set omega and Z is the direction, we denote by x of x0 zt. So the ray issuing from x0 at time 0 in the direction Z, and which propagates according to the law of geometric optics. I mean that it will be reflected along the boundary of omega, okay? And as we will have many reflections, so we denote them. So Ti is the reflection time corresponding to I, and we denote by xi the corresponding point in the boundary. And we can compute actually very easily the new direction of propagation. It is given this way, where n is a normal to the boundary of omega at xi. So a very simple picture. So assume that our set omega is just this set in purple. So we start with x0. This is the first direction. So this is the way, and okay, we have a reflection here. So we'll have the point x1 at the time t1, and we will have a new direction for the propagation, which is given by z1. We continue. We arrive to this point where we have again a reflection. It is denoted x2. It is at the time t2, and we have a new direction for the propagation. Okay, so this is the way the ray propagates in the domain. Of course, this is a picture for square, but actually we have to think about a domain which is a curve, okay? But something which is more complicated. So we have to define what is epsilon. I remember you that we have epsilon, which was 1 or -1 is the formula for the half space. So how to define it? So when x0 is given, and when z is the direction and t is the time, we say that epsilon at x0 zt is -1 to the n, where n is the number of reflection undergone by the ray in the time interval 0 capital T, 0t. Okay, so if you look at this picture, so in this half space, so at the beginning, so there is no reflection, so epsilon is 1. Here you have one reflection in red, so epsilon switched to -1. But also here we have -1. Okay, so you have it, and here you have another reflection. So it is a second reflection. So on this part, epsilon again is 1, and so on, and so on. Actually, you have a sequence. It's not a finite sequence. It could be sequence. And okay, so now to justify all the computation, actually, we would like that there is only a finite number of reflection in some interval 0 capital T. And it turns out this issue was investigated by people working in billiard dynamics a long time ago. So I will introduce some assumption and relate to the results that are known. So I denote by O the domain of the map X, and we should make some assumption about our open set omega. The assumption capital A, which tells you, yes, you have some time capital T, such that the rays undergo at most a finite number of reflection in the time interval 0t uniformly in Z. That is, for any x0 in the domain, the supremum for all the direction Z in S2 of the number of reflection is finite. Okay, this is some assumption. So a finite number of reflection and uniformly with respect to the direction. If you look at the ball, you can prove it's quite easy, actually. Actually, the dynamics is in a plane, actually. It's very easy to see that you have a finite number of reflections, and actually all the angles are the same, so it's very easy. But in dimension 2, so in dimension 2, it was noticed by Alpern in 1977 that you could have infinitely many reflections close to a point where the curvature vanishes. So even if the domain is convex and smooth, you can have some problem. You can have infinitely many reflections around some point. Okay, so we have to be very careful, very careful. Hopefully, okay, we were able to prove in dimension 2 that if the curvature is strictly positive along the boundary, we don't have this. Okay, so this is a result, and actually it's true for any time capital T. So in dimension 2, which is if you take the domain which is strictly convex, that is the curvature is strictly positive, for any x0 and any time capital T, the number of reflection is finite uniformly in the direction Z. And to prove that, actually, we use a tool, which is very classical in this kind of literature about billiard dynamics. So we use a dynamical system xn+1, cn+1 equal t xn cn. And actually, Latzytkin introduced a very nice coordinate to represent this system. And using this coordinate, we were able to prove that. Okay. For the moment, we don't have some equivalent result in dimension 3. What we expect that it is probably true if the 3 principal curvatures are strictly positive, but for the moment, we don't know that. Actually, because we need to have some coordinates like those of Latzytkin, but in dimension 3. And for the moment, we didn't find them. So the main result is the following. So we have a formula, a Kirchhoff formula to represent the solution for the wave equation in a bound and open set that satisfies our assumption A. So we consider initial data quite reasonable. So they are sufficiently regular and they are null on the boundary of omega. Then the solution of the wave equation with a homogeneous Dirichlet boundary condition is given this way. So you recognize the two terms. So we integrate actually again along the wavefront because x of x0 zt describes the wavefront issuing from x0 at time t, okay? And we have again the function epsilon. So with our assumption, epsilon is piecewise constant. So we don't have infinitely many switching. So we can give a sense and actually we can justify this formula. Actually, we start from this formula and we prove that, okay, it is indeed the solution of our system. This is the way we did it. So this is the Kirchhoff formula. And thanks to that, we have this kind of Huygens principle. So if we denote by theta the support of u and ut, we can say that theta is at time t is included in the set of point x0 such that the wavefront corresponding to x2 at time t intersect the support at time 0. And now, okay, we can apply it to the control problem. Of course, we will not recover this way Bardos-Leboroch result, but we will have some result which can be useful for numerics, and this is the goal, okay? So here we have two sets. So here I keep the same notation. Now omega is a big set on which we will do the numerics, and omega prime will be the small set for the control problem. Okay, so omega prime is included in omega. So we consider some initial data which are smooth and they vanish at the boundary. We assume that the support is in the small in the closure of the small set omega prime. And although some assumption, we assume that the wavefront leaves omega prime at time capital T. This is okay, what we need. It is a sort of quantitative version of Huygens principle. Okay. Then, when we solve the problem, the control, the system of the wave equation with a directly boundary condition on the big domain omega, we know that in the small domain omega prime, it is 0 at time capital T. And so, if you take the restriction to omega prime time 0 capital T, okay, you solve your control problem. And for the control, you just have to take the trace of your previous solution to gamma 0. How many times do I have still? How many times? Please? Oh. Bon.
15 minutes.
Okay. Bon. Okay, so now for the numerics. So we did numerics not using finite element with meshes because it's quite difficult to do. So we tried to do numerics just by using spectral method in box because it works well. And so we have first simulation, but it is still a work in progress. So we consider a system some open set omega, which is included in this set where f is some smooth function, okay? And we assume that the part on the boundary where there is no control is included in the graph of f, okay? So we can look at, for instance, some parabolas, something like that, okay? So we want to simulate, of course, the wave equation in the big domain with Dirichlet boundary condition, okay? Okay, so to do that, so we want to use a method in box, and so we have to strengthen this surface. So we want to have a plane instead of the surface. Okay, so the way to do that, of course, is to make a change of variable, of independent variable. So we keep x1 is y1, x2 is y2. Okay, but for y3 we take just the difference. Okay, of this guy, and so. When you are in this surface, it means that y3 is -1. Okay, -1. Perfect. So we will be able to work in the box -1, 1 to the 3. Okay. Of course, when you do this kind of change of variable, you have to pay something. So the wave equation will be transformed into some hyperbolic equation with variable coefficient. You have to pay with that, but you can compute the variable coefficient. They are given explicitly in terms of f by this formula. Just computation, just a computation of a derivative. It's absolutely not difficult. So what we want to do numerically now, you want to solve this wave equation with variable coefficient. It has to be 0 on the so omega tilde is a box. It's -1 to the 3. Okay, the solution has to be 0, and you start from u0, u1. Alors, so to do it actually, so you have to look at the discretization in time and discretization in space. For the time we use, which is quite usual, so leapfrog formula, it's very classical. And now for the discretization in space, as I told you, we didn't use mesh and finite element. No, we used Chebyshev spectral method on the tensor product grid in y1, y2, and y3. So we in some sense, we can compute the derivative by using spectral method. And this kind of thing are well described in the nice book by Trefenton, Spectral Method in MATLAB. Okay. And okay, so I will present to you two simulations for that. So we start with the box. So for the box, there is no change of variable. F is 0. So just to see what happens if it works well. Okay. And so we took some Gaussian for u0 and u1 is 0 still. And the Gaussian, we can cite actually that it has a support in the ball, numerically at least, in the ball centered at m and of radius r. R is 0.2 and m is this point. So actually the support is close to the boundary y3 equal -1. And this is what we want to have. So a support which is close to the boundary, and to see if we have the good reflection, if Huygens principle is satisfied, and so on. Okay, so again, we make a cup of the solution. So we say that y3 is this value. We just look at the solution for this value of y3. And of course, the zone of interest is the zone around the origin. So actually, just a neighborhood of the Gaussian, the support of the Gaussian. Okay, so we have to look at what happens here. And again, so we did the numerical computation of the L infinity norm. Here we took the balls onto that at M and of center R. And what we see, okay, we have some evolution which is quite similar to what we obtained with the Fourier series before, quite similar. And we see that there is a zone where the L infinity norm is almost zero, actually. It's almost zero. Here's the minimal value. We find a 2 times 10 to the minus 3, so it's very small. Okay, but after some time, it's not zero, and it's absolutely normal because we have waves, and the waves arrive to the boundary, and after they go back. Okay, they go back, so you have bands, and so you have reflection of the waves, and after some time, we can have something which is not zero at the origin. It's quite normal. So it means that the time of the control for the simulation should be selected with in this zone. Okay, so we have the null contrariety in this zone. So another simulation now with a real boundary which is not flat. So we took the case of some paraboloid. Omega is included in this set. So now we have a real coefficient. So we just compute all the coefficient A, B, C, D from the above formula. It's quite easy. We took exactly the same value. I have to say something about that. So we took n equal 34. So we have 34 points in each direction. And so actually we have this guy 44 to the 3. And it turns out actually, it is on a small lab tab. So if we increase the value, we can have some problems. So actually, we have to decrease the time step, and otherwise we can have some instability problem. And so the computations are not as good as before as for the series because we have less points. This is important. Okay, and so we take exactly the same initial data, and we obtain the following, quite similar to what we obtained for the box. So this is the initial Gaussian, and you see that at the time 1.2 around the support of the Gaussian, it's it's almost zero, so it's good, even if it is not zero close to the boundary. And if you look at the L infinity norm, the value is quite small. It's 5 times 10 to the minus 3 at 1.2, something like that. So it's quite good. So it's time now to compute. So Huygens principle, which is known to hold in R3 but not in R2, can be used with some success to recover some control result for the wave equation in subdomains of R3. We prove it quite easily in half space. It was enjoyed work with Carol Rosier, and also we extended it to certain strictly convex domain by first proving some extended Kirchhoff formula. And so, this approach gives numerics for the control of the wave equation in dimension 3, which is quite difficult to do. If we try to do it with HON, you can have some difficulty because it is the dimension 3. So what remains to be done? So first, at the theoretical level, we would like to see if assumption A is valid for strictly convex domain. So we would like to justify it. Now, we would like to see if Huygens principle also is true for domains which are not convex. Maybe it's true, actually. But we have, of course, to assume that there is no trapped wave, because if you have trapped wave, there is no chance to have a Huygens principle. And another issue is, can it be proved without Kirchhoff law? It would be interesting to see that. Another things to do is to do numerics with finite element. That is a big deal. We have to be honest, it's difficult in dimension 3. And also, in the long time, it will be nice to see if we can find transparent boundary condition in dimension 3, similar to the transparent boundary conditions that we had in dimension 1. Thank you, and sorry for the delay.
Okay. Thank you, Lionel, for this wonderful talk. And we have time for questions. Oh, and the audio is open for questions. Okay. Okay, so if not, thank you again, Lionel, for your very nice talk.
Thank you for the invitation.